One very important and useful technique that is used in analytical chemistry to study molecules is known as infrared spectroscopy. Now, infrared spectroscopy uses electromagnetic waves in the infrared region to basically study and determine the different types of functional groups that are found on different types of molecules. So how exactly does infrared spectroscopy actually work? How exactly does it use infrared electromagnetic radiation to actually study the different types of functional groups that exist on our molecules? So let's begin by basically briefly discussing the theory behind infrared spectroscopy. Now, of course, it's much more complicated than this, but for simplicity purposes, we're basically going to just go over the important points. So, in the same way that an electron can gain just the right amount of energy and transition from the ground to the excited state, a certain molecule can gain just the right amount of energy and transition to the higher molecular energy level. Now, if we examine any molecule, we see that molecules consist of atoms, and those atoms are held together by chemical bonds. So let's imagine that we have two masses. So we have mass 1 and mass 2 that are connected by a spring. If we take those two masses, stretch them out and let go, those masses will begin to vibrate, to oscillate back and forth in simple harmonic motion with a certain frequency and a certain vibrational energy. Now, in a very similar way, we can imagine that atoms held by chemical bonds oscillate or vibrate back and forth in simple harmonic motion, and they oscillate with a specific frequency. So, different types of chemical bonds and different types of atoms basically oscillate with different frequency values, and because frequency determines the energy, we see that specific chemical bonds have specific vibrational energy values. So how exactly is this important? How exactly can we relate this to infrared spectroscopy? So let's look at the following diagram. So this is the y-axis. It represents energy. As we go higher, the energy increases. Let's suppose we take some type of molecule. So we have the following molecule that has a certain ground energy. So we have atom 1, atom 2 held together by a chemical bond, and it basically vibrates back and forth with a certain frequency value that corresponds to this type of chemical bond. Now, if we had a different type of chemical bond, the frequency would be different. So let's suppose we have this vibrating or oscillating chemical bond, oscillating molecule. Now we take infrared electromagnetic waves and we allow those infrared electromagnetic waves to basically hit the following molecule. Now, if the frequency of oscillation of that infrared electromagnetic wave is not the right frequency, does not match the frequency of oscillation of this molecule, then that means that electromagnetic wave will not be absorbed. In fact, it will be transmitted through the molecule and will continue moving through space. However, if the frequency of the electromagnetic wave is just right, if it carries just the right amount of energy, then it will be absorbed by our molecule and the molecule will transition to the higher in energy molecular quantum energy level. So basically, the energy of the ground state is shown here, the energy of the excited state of the molecule is shown here. Now, when it transitions back to the ground state, it will release a photon of energy. It will release infrared electromagnetic radiation. And that infrared electromagnetic radiation can then be collected by our infrared spectroscopy machine. And so those energy values that are contained within this radiation can then be collected. and that way we can analyze the different types of chemical bonds and the different types of functional groups that exist within that molecule, because different functional groups have different chemical bonds that have their own specific frequency values, and that means they have their own specific energy values. So this is how infrared spectroscopy basically works. Now, of course, things are a bit more complicated if we look at the details, but we're not going to concern ourselves too much with the rigorous details in this lecture. So basically, this is how it works. Now, let's move on to something called the wave number. The wave number is very important when we're dealing with infrared spectroscopy, as we'll see in just a moment. So let's begin by recalling the relationship between the frequency of oscillation of any wave and the wavelength. So it depends on something called our speed of light constant c. So the speed of light in a vacuum c is equal to the product of the frequency given by v and our wavelength given by lambda. Now in physics, the frequency is usually given by f, but when we're dealing with infrared spectroscopy, we usually use a v to designate the frequency. Now c is the speed of light in a vacuum given by this quantity. So in physics, our wavelength lambda is usually given in meters, but whenever we're dealing with infrared spectroscopy, our lambda should be given in centimeters. So let's take this equation, let's rearrange it and solve for our frequency v. The frequency v is equal to 1 divided by lambda multiplied by c. Now we can define a quantity known as the wavelength that is given by v with a squiggly line over the v in the following way. The wave number is given by 1 divided by the wavelength. Now, what exactly is the physical meaning of the wave number? What does it actually mean? Well, it turns out that the wave number designates the number of wavelengths found in 1 centimeter. So because our wavelength is defined in centimeters, we see that the wave number is given in the reciprocal of centimeters. So centimeters to the -1. So basically recall that frequency is simply the number of oscillations made every single second, and our wave number or our wavelength is basically the distance between any 2 consecutive crests or any 2 consecutive troughs. Now, if we take this equation and replace 1 divided by lambda with simply the wave number, we get this important equation. So this is the relationship between the frequency of oscillation of our molecule v and the wave number of that molecule given by v with the squiggly line. So we see as our frequency increases, the wave number also increases and our wavelength decreases. Now, since molecular vibrations follow harmonic motion, we can basically use Hooke's law to develop or derive an equation, and this equation is given in the following section. So the frequency of oscillation V is equal to the product of K, the spring stiffness constant of the bond, multiplied by the square root of F, which is the force constant, and M1 plus M2 divided by M1 multiplied by M2. So this is known as the reduced mass, and it comes from physics. So basically, what exactly is the meaning of this K? Well, the K is the spring stiffness. It designates, it basically correlates to the strength of our bond. So the stronger the bond is, the higher the spring stiffness constant is. Now, M1 is the mass of atom 1, and M2 is the mass of atom 2 within that particular chemical bond. So this equation basically tells us that the frequency of vibration of any chemical bond depends on two things. It depends on the masses of our two atoms within that particular chemical bond, and it depends on the strength of that bond. So we see that the stronger our bond is, the higher the strength between our two atoms is, and the higher our mass of those two atoms is, the greater the frequency of oscillation of vibration of that particular chemical bond. And because of this relationship, the greater the frequency is, the greater the wave number is. So we see that molecules with strong bonds can absorb radiation with high energy, because strong bonds means a high frequency value, and because energy is given by frequency times Planck's constant of any given photon of energy, the higher the frequency is, the more energy that chemical bond can actually contain. So we see that generally speaking, the stronger our chemical bond is, the greater the frequency of vibration, the greater the wave number is, and the more energy that our chemical bond can actually absorb. The weaker the bond strength is, the lower the wave number is, the lower the frequency is, and the less energy it can actually absorb when we direct that infrared electromagnetic radiation at the chemical bond. So to see exactly how infrared spectroscopy actually works, let's take a look at the following example. Let's suppose we take a certain molecule, the cyclohexanon, as shown in the following diagram. So this molecule has three types of bonds. We have the CH bond, we have the CC bond, and the CO double bond. So that basically means when we take this molecule and place it inside the infrared spectroscopy machine and direct the infrared electromagnetic radiation, we should basically see three different types of peaks. And this can be seen in the following graph. Now, whenever we're examining the graphs of molecules under infrared spectroscopy techniques, the y-axis designates the percent transmittance, and the x-axis designates our wave number that is given in the reciprocal of centimeters. So basically we see that the higher we go along the y-axis, the more transmittance takes place, and the less our chemical bond absorbs that energy. Now, the lower we go, the more energy that chemical bond actually absorbs. Remember, different chemical bonds have different frequency values and so can absorb different amounts of energy. Stronger bonds can absorb more energy and so have a higher wave number. So let's compare the CH bond within this and the CC bond. So CC bond, the bond between carbon and carbon, is lower in energy. So basically, because the CC bond is weaker than the CH bond, that means the CH bond will absorb more energy, and that means the wave number for the CH bond will be greater than the wave number for the CC bond. Now let's examine the COO. So we actually have two different peaks for our COO. We have this peak, which basically corresponds to the ground state of the COO bond, and we have the overtone band. So this overtone band simply designates the fact that when our COO bond gained that energy, it basically transitioned into the higher in energy level, and this corresponds to this overtone shown by this peak, which corresponds to a wave number that is much greater than in this case. So once again, this graph basically describes our different chemical bonds, our different functional groups. And what infrared spectroscopy actually does is it directs infrared electromagnetic radiation at the different chemical bonds that exist within our molecule. And those different chemical bonds absorb different amount of energies with different frequency values, and so we can basically try to determine what the different bonds are using these types of graphs.